physics kids. So I'm going to try and do this between a couple of screens in terms of simulations and math and diagrams and pictures and the whole smash. Okay, so this is out of this FET simulation. And what you have here is two bulbs that are in series. So you got bulb number 1 and then you got bulb number 2, okay? And this battery is a 10-volt battery, and each of the bulbs has a resistance of 10 ohms. So, and this is on your equation sheet, and resistors or bulbs that are in series are added together. If they're in parallel, which we'll get to in just a second, then you add the inverses of them. So this is, for now, just pretend like this middle section doesn't even exist. So right now I've got two bulbs that are in series, and my little amp meter down here is showing 0.5 amps. So this is why that works. So if you go to notability, and this is what I've got showing right here. So what I've got is that I've got bulb A, which has a resistance of 10 ohms. And then I've got bulb B, A and B, which is also 10 ohms. So because those are in parallel, I'll take 20, excuse me, I screwed that up. I was one step ahead of myself. I'm going to take 10 ohms plus 10 ohms, and I'm going to get 20 ohms. So this is what's known as the equivalence resistance. So in other words, having two 10 ohm bulbs in series is the equivalent of having just one 20 ohm bulb or one 20 ohm resistor. So, and that's one of the key things that you've got to be able to do, is be able to figure out the equivalence resistance. So when you look at that current, you know that you have Ver. So this is your kind of your go-to equation. So I know the voltage across the battery is 10 volts. 10 volts. And the equivalent resistance is 20 ohms, so that gets a current of 0.50 amps. So that's why that is what it is. Because it's like having, even though there's two different bulbs, it's like the equivalent of having one 20 ohm resistor in there. And therefore, that's why we have a current of 0.5 amps. So, and with this one, no matter where I put that amp meter, because everything is in series, and it's just one simple circuit, then everything remains the same. So now what I'm going to do now is that I'm going to close this switch, which now raises that current to 0.67. So now I've got one bulb in parallel, and I've got two bulbs that are in series. Now notice that this bulb up here got quite a bit brighter, okay? Because that's pulling 0.67 amps, whereas before it was pulling 0.5 amps. So we'll get into the math on that a little bit later on why that happens. So I got 0.33 amps here. I got 0.33 amps here. I got 0.67. So this is actually kind of a rounding error rounding process. So notice that because of Kirchhoff's rule, if that's 0.67, that becomes 0.33, and that becomes 0.33, which adds up to that. So now let's do a little bit of math here and figure out why that is actually 0.67. So now, let's go back to my notability, and I think it's this one. Okay, so here's what we've got. So now when you look at this, this becomes a little bit more complicated in terms of the math, although not horribly. And I think we can overcome this pretty easily. So what we have here is that we're saying, okay, that's like saying I've got these two bulbs here that are in parallel, okay? So these two bulbs are in parallel. So what I've got there is I'm going to take 1 over 10, because they're in parallel, plus 1 over 10, and then that becomes 1 over the total resistance, and so that my total resistance then is 5 ohms. So now, here's what's happening. I've got these two here, because they're in parallel, would be like the equivalence of having one 5 ohm resistance. So this is going to be important. When you put things in parallel, your overall resistance goes down. So then if I take that 1 over, because now I've got this 5 ohms, and then I add that to that 10 ohm resistor, or bulb, which is this one, okay? So then I get a total of 15 ohms. So having these two bulbs in parallel with that one bulb in series, then that's like saying, oh, this is the equivalent of having just one 15 ohm resistor. So then if you go to Ver, then I've still got a 10 volt battery here. Then that's like having a 15 ohm resistor. So if you take 10 and divide it by 15, you get 2/3, so you get 0.67 amps. So this is why this becomes 0.67 amps. So, but here's what's important again. When we had the two bulbs in series like this, we had the 0.5 amps. Once we add another one in parallel, then the current goes up and you get 0.67 amps. So this is why, like in your house, if you tend to run a lot of things, you have a lot of things going on at the same time. Maybe somebody's got like a space heater going on and a blow dryer and a vacuum cleaner. What will happen is that you'll throw a circuit breaker, because what happens is that the circuit breaker can only handle so much current. And so when that current exceeds that limit, then that breaker throws, hey, you got to go down and reset it. So because your house is in parallel, the more stuff you run, the resistance goes down. As you drop the resistance, the current goes up, and because you got the same voltage of, in this case in your house, it's 120 volts. So that's the overall idea with that one. Now, one of the questions on your assignment is going to be question number 6. So for those of you that tuned in for the show, you already know this, and I'm just going to give you a brief summary for those of you that weren't there. So here's the situation. You got two bulbs in series, and then you have just a wire here and a closed circuit that's open. So the question is that we're going to close this switch. We're going to allow that electricity to flow through. Now, what all of your colleagues agreed to was that nothing happens to bulb A. Bulb B becomes dimmer because some of that electricity is going to flow through this. So that's what everybody agreed to. Don't let them tell you differently that, oh, we had the right answer all the time. No, you didn't. It was a bold-faced lie. And some of you are going, oh, I really thought that, whatever. Okay, so here's what actually happens. So when you close this, these wires have no resistance. So that current is still flowing through here, and then all of a sudden, bam, it takes this path because it's easier. None of it goes over here, and it goes through. Now, this is a pretty idealized case where there's absolutely no resistance in the wire. In reality, what will happen is that this is going to have some resistance, and you will continue to put a little bit of current through there. But in this situation, this is assuming a completely idealized situation. That current will flow through here. That bulb becomes brighter. Now, here's what's important. So this is 1 amps. If you go back to when they had both bulbs, because again, these were in series, then that current was 0.5. So this goes back to how your mom cooks. So if your mom cooks in series, that means that the voltage is going to stay the same, but because you're cooking in series, then your resistance actually goes up and the current goes down. If she cooks in parallel, where everybody gets the same amount of food, then the current goes up and there's more food flowing out of the kitchen. So just kind of a random thing and about how mom can cook. So again, this is just showing this Kirchhoff's law. So this is back that one where we had the two in parallel. And quite frankly, I've lost track if I've gone over this. But anyway, so what you have here is 0.33 amps. This part here was 0.67 amps. Okay. And so when you look at this is 0.33, that's going to be 0.33, that's going to be 0.67. So here's what you need to know for today. So on symbols, you can, typically what you see in circuits, you're going to see kind of four big things. You're going to see a switch, okay, which is, hold on, let me back up. So you can have a switch like this, okay, so it would be something like this. You can have a capacitor, okay, and you all have seen those. Capacitors act to store energy, okay, you can have capacitors. You can have light bulbs, okay, typically shown like this. You can have resistors like this, and then I take that back, there's actually 5 things. And then you can also have like a battery, okay? So those are what you're going to see most often. Switches, capacitors, batteries, bulbs, and resistors. So with your capacitors, and here's the difference between capacitors and batteries. Batteries, you have like a tall side and a small side, and capacitors, the two are the same. So with all of that said, I have texted or sent out an email with the assignment. And let me give you a hint, when you get to questions 12 and 13, that's going to require some algebra. 12 is a series of things that are questions that are relating to things that are in parallel. And then the same thing is going to happen on 13. You have some parallel, but then it's going to ask you what would happen if they were in series. So that'll make sense when you get to those questions. So let me give you some hints. Your answer to number 12, if you do that right, should be between something around, your answer to number 12 should be around 12. That's a huge ish, but it should be around 12. And your answer to number 10, both those answers to number 10 should be around 10. But other than that, you're on your own, so I'll get this video uploaded. And if you all want to have a Google Meet session on Wednesday, because that's when this is due, I can make that happen. So anyway, that's the story. Talk to you later, kids.